Okay, so in this video we're talking about a special type of sequence called a geometric sequence. And pretty much a geometric sequence is any sequence that has a common ratio. So a sequence is geometric if there's a number r called a common ratio and again, like with the arithmetic sequences, it can be written two different ways, and it's all based on what position did you start with. If you started with the first position, then you're going to write the geometric sequence this way. If you start with the 0 position, then you're going to write the geometric sequence this way. So we're going to do it both ways in this example. So in this sequence right here, which is just an ordered list of numbers, we want to create we want to state the initial term, common ratio, and then write the closed form definition or the formula, however you want to say it, for the geometric sequence. We want to start off first with the first position. So I'm going to pretend that this is the first position. So what that means, if I'm doing the first position, then the geometric sequence is going to use this rule. The first value times r to the n minus 1 power. Well, the first value is 3, so g of 1 is 3. My common ratio, I find that by dividing, so 9 divided by 3 is 3. 27 divided by 9 is 3. 81 divided by 27 is 3. So my common ratio is 3. So what that means is, when I plug in, the geometric sequence is 3 times 3 to the n minus 1 power. What that means is, if I start off by plugging in a 1 here because I started in the first position, you can't do the 0 position because I started with the first position for this sequence, starting with the n equals 1 for the first position, and then keep going up with my n values, n equals 2, n equals 3, n equals 4, then I'm going to generate every value in this sequence. Let's do it again with pretend we're starting at the 0 position. If I call this the 0 position, then I'm going to use this rule. G of n is just the value of the 0 position times the common ratio to the n power. Okay? So, my value of the 0 position was 3. My common ratio was still 3. That hasn't changed. So now I'm just going to plug in what I know. So the geometric sequence, if I start at the 0 position, can be written as 3 times 3 to the n power. These two look almost identical. The only difference is here, when I start in the 0 position, I have n. When I start in the first position, I have n minus 1. So if I'm starting in, if I say n equals 0, since I pretend that I started in the 0 position, then I'm going to generate this sequence. If I want to start in the first position, I have to use this format. Okay, so it's just, again, based on what position you started with. I wasn't sure, based on this example, it didn't tell me, so I did both, just to be safe. Now, what we're going to do is, so we've already looked at a geometric sequence, which is just an ordered list of numbers that has a common ratio. Now we want to look at the series associated with a geometric sequence, just called a geometric series. Remember, anytime we're talking about series, we're talking about adding up all the values in the sequence. So, a geometric sequence, geometric series, and it looks like this. Again, capital G for geometric series is just simply the sum of all the values in the geometric sequence. So what you have to do first is find the rule for your sequence, then use sigma notation, and then find the closed form definition that represents your series. Okay, so consider the geometric sequence little g. Little g starts in the 0 position and has an initial value of 4. What that means is g of O, the g of 0 is 4. So in our starting position was the 0 position, and it has a value of 4. Since we're starting in the 0 position, then our rule for our sequence, little g of n, is 4 times the common ratio, which we're told is 2. 4 times 2 to the n power. Again, look back on the previous slide, so rewind it a little bit if you're not sure how I'm getting this, since I'm starting with the 0 position. So, now what we're going to do is use this. This is our geometric sequence. And we're going to use that as a model to find the geometric series. Again, our variable on the bottom of the sigma notation must match the variable that we're plugging into our sequence. Okay? So when we write it, our series, our geometric series, is going to be sigma from k equals 0 to n of 4 times 2 to the k. When you first start off, these two variables must match. Everything's the same here. Our sequence is still plugged into the sigma notation. It's just we had a k on the bottom, so we have to use k here instead of n. That's the only difference. We're going to finish off when we create the closed form definition. All our variables will be n, so everything will be fine. Okay, so now what we're going to do is to create a closed form definition for this series. So again, 4 is a coefficient, it gets to come out. So 4 sigma, starting in the 0 position, going to the n position of 2 to the k. Now, we had a rule for this. It was called Euclid's method. We haven't done a lot with Euclid's method, but it does have a rule. So pretty much, it all is based on whatever letter or number is on top. Here we have an n on top. So this sum is going to become, the coefficient of 4 just comes down. It's 2 to the n minus 1 minus 1 divided by 2 minus 1. Okay? And that's our rule. Now, this is very hard to clean up, so I'm going to leave it alone. But this is g of n. So g of n equals this. So again, n is our input, g of n is our output. So we're finding, once we know what n is, we can find specific outputs for our series. And series just means we add those outputs together. And that's it for this video.